So guys, in this specific workshop we're going to use regression with experimental data from NIST of methanol benzene system. And what we want to do is to first verify the data, second model with Peng-Robinson, and third eventually get some parameters based on the experimental data using regression. So the first step I want you to do, guys, is to use a activity model and experimental data and see how it fits the data. Benzene and methanol. This is Wilson. Remember that this might take some seconds or even minutes. Okay, now it has been loaded. What we want to get is the binary vapor liquid equilibrium data on constant pressure, so we only need this one. There are plenty of data points that you might find, but the one that we are going to use is this one right here, PLE 121. Now ensure that this is the actual source, so you don't mix, because whenever Aspen has new modifications or the NIST TDE engine changes, it will change the name. So select this one, save the data, and what I want you to do is to make your theoretical TXY analysis using Wilson model, methanol. Okay, using Kelvin. No, actually I need the reverse. Methanol was fine. Okay, so now what I want to do is to merge this plot with the data. So where is the data? The data is right here. So let's make a TXY diagram and merge this with this right here. Use the same y-axis, that's why I changed to Kelvin. And this is our theoretical model. So if I wanted to model with Wilson, we will have pretty good fit. But this is not the scope of this workshop. What I want to do is use Peng-Robinson model in order to model this. So first things first, let me go and use Peng-Robinson. We already proved that Wilson is a good model. Let's see how it goes for Peng-Robinson. Some parameters, retrieve parameters, okay, and okay. So once that we have retrieved the parameters, I want you to change this Wilson to Peng-Robinson and see how it goes. So remember that Peng-Robinson is much more of an equation of state model. It's not modeling that smoothly our data. So let's go back to our data. Let me clean. This is the experimental data. Okay, so let me just away, take this away. Okay, oops. Once again, let's get the diagram from Peng-Robinson, and what I want to do is to merge the data plot into here. Oops, I need to use Kelvin, so that's very, let me use SI systems, and from here use Kelvin, and now plot data into the binary equilibrium, use the same y-axis. And as stated, guys, this is very not a good fit. Remember our Wilson model was very good. It had some points that were not that exact, but in general it modeled the azeotrope near the 65%. Here we have a very bad fit, and the isotrope comes from 90 to 95%, and it models very high temperatures. So one thing that we can do for this is to use regression to get a parameter. So let's do that. Let's go to home. Let's go to regression mode, create a new regression. Peng-Robinson is what I want to get parameters from, and this will be the data set. Let's go to parameters, and in this case, let's see how it goes if we only add one PR key KB value. Element 1, benzene, methanol. So we're ready to set the regression. Ensure that you have regression run, and it's done. As you can see, let's repeat this analysis. Let's run analysis. As you can see, guys, our Peng-Robinson has been modified. If you remember, before we had the isotrope at 90 to 95%, and now we have it between 65 and 70%. Now let's merge our experimental data to the fitted data using the same y-axis, and definitely is much better. The temperatures are not that high, but yet we have a isotrope not in 60 to 65 but to 60 to 70. Also, these are not good fitted. Also, these temperatures are not well fitted. So what I'm going to do is to go once again to regression. Let me go here, input. Let me review why fit pass, why didn't it work. And it didn't work because we had 34 as the residual root mean square error. We want to achieve less than 20 or even 10 points. So let's see if we can do that. Let's add an extra binary parameter for the regression. So this was the first model, very bad fit compared to the isotropes. This is the first regression, still a little bit far the isotrope, and what we're going to do is add this one right here and see how it goes. Okay, now let's run. Ensure that you have the regression you want to run. And now, because it has been changed, Aspen Plus will prompt us if we want to modify this. So let's choose yes and see how it models now. Same thing, we're going to go binary analysis, and actually you can create a new binary analysis. It will be binary number 2. It's exactly the same than this one right here, but in this case we're going to use the new Peng-Robinson data. Okay, so now with these two parameters we have a much better approximation to the isotrope, which is 60%. Now let me merge the experimental data to my new plot and I use the same y-axis. As you can see, guys, we are getting each time near to that. Now one question will be, why didn't we got this estimation? It's because of the lower and upper boundaries. And you can continue adding more, for instance PRLU or LIAA. So I would definitely recommend you to repeat this workshop using the same data and see the error. Try to verify the data and try to make a better fit. Why does it didn't work? Why isn't this fitting this correctly? Is it because of the plot right here? Let's see how it goes. Oops. Yeah, still the same data will not fit correctly. So let me go and change to analysis and rerun this. let me compare Wilson model now with. So let me plot this with number 2. And as you can see, Wilson model is now pretty similar to that of the Peng-Robinson modified model. And let us add the data. So as you can see, the Wilson model is still a good fit. So if you ask me, I would rather use my Wilson model data than my Peng-Robinson estimations. But as stated before, guys, your homework will see to increase or improve the regression and see if you can actually convert a Peng-Robinson model to a Wilson model fit. So now be careful with the Wilson data, because sometimes we have data which is not okay, or it has plenty of error, consistency, and you are working too much towards the regression, and you will end up getting the conclusion that actually the experimental data is incorrect.